If you were to look at the synopsis of the talk, you will realize, see, origin of the universe, origin of the earth, origin of life, of course, they are all very, very exciting subjects. But all of us know what distinguishes us from other forms of life on earth. One thing is bipedal motion. We have two hands which are free. And that's what Professor Ramakrishanan starts from, okay, in his lecture. And these two hands are free. And humans have made tools out of materials which are available. And over a period of time, not over a period of time means not years, over thousands of years, even hundreds of thousands of years over that, tools have been perfected and the properties of the materials, naturally occurring materials from which tools are made, their properties have been improvised. At the same time, in the modern era, new properties of the materials are being looked into to further improvise things. All these things are for our benefit, to be dominant over all other forms of life on this earth. Anyway, Professor Ramakrishanan, I'm sure he'll talk about all these things in a very interesting way. I don't want to come in your way between you and Professor Ramakrishanan. Let me introduce Professor Ramakrishanan. Okay, formally, Professor Ramakrishanan completed his graduation from the University of Bombay, now Mumbai, MSc from Indian Institute of Technology, Bombay, IIT Bombay, and his PhD is from, of course, fantastic place, University of Massachusetts, Amherst, USA in 1988. After a 2-year postdoctoral stint at Corporate Research Laboratory of Exxon Research and Engineering Company at Annandale, New Jersey, in 1990, he took up the faculty position in the Department of Inorganic and Physical Chemistry at the Indian Institute of Science. And he has held many posts there, important ones. Now, at Indian Institute of Science, he first served as the division chairman of Chemical Sciences, and later as one of the deputy directors of the institute itself. Of course, many accolades and awards have naturally come to him. He was awarded the prestigious SS Bhatnagar Prize for Chemistry in 2005, and he was a J.C. Bose Fellow during 2011 to 2021. He served as the president of the Society for Polymer Science in India, SPSI, from 2015 to 2022. What is more important, his research interests are in the design and development of novel polymerization methods, hyperbranched polymers, polymerization and hardened media, internally functionalized porous polymers, reactive coatings, and so on. And he was an associate editor of the Chemical Communications for a decade, important, and he has served on the editorial board of Macromolecules, ACS Macro Letters, and Polymer Chemistry. So, thank you, sir, once again. The stage is yours now. Please welcome Professor S. Ramakrishnan.
Thank you very much, Guru Prasad. Thank you very much. This is not required. Yeah, I have this mic, so thanks a lot. It's a real pleasure for me to be here and give this public talk on this. And as Dr. Guru Prasad mentioned, it was an interesting idea. Come. So it was an interesting idea to have this origin series, So I was given this topic to speak on, origin of materials properties, and I realized that it was an attempt to link these series that gave this birth. And I thought the first 3 talks were really very interesting titles, and I think the audience must have certainly enjoyed it immensely. So origin of materials properties, origin of materials, and with the emphasis of properties is what the title is really. So I think I'm a polymer chemist myself. That means I work on a small subsection of polymers that are of materials that have become more interesting in the last century. Okay, so I'll touch upon that towards the last part, but the early part of the talk will really be sort of a historical, as developing some historical insights into how materials developed and how human society dealt with that. So, since this is an LED screen, so I can't use a laser pointer, so I am going to use this. So, pardon me, I will have to stand here and speak. Okay. So, laser pointer is really kelsa madalla, LED light emitting, so it won't work. So, that's the title. So, let's go to the talk. So, the need for materials, as I summarized and Dr. Guruprasad mentioned also, it's interesting that the progress of humans in general has constantly moved up as materials have developed. So, in other words, you can turn it around and say that as we develop improved materials, we also improved our life. Okay. So, there is a very strong correlation between the way we live, societal development and materials development. As is, there is a correlation between energy consumption and the development stage of a society. There is a correlation between how much per capita energy consumption humans consume and also the state of development of society in some sense. Okay. So, people have developed that. So, similarly, there you can see that as we progressed, we have constantly developed new materials, or you might say as we developed new materials, we actually progressed. Okay. So, that means there is a very close relationship between these two things. Yeah. So, okay. So, in the early stages, we've primarily our focus was on utilizing naturally occurring materials, right. So, naturally occurring materials can be of two types when you look at our forefathers. Is it going? Yeah. Okay. Thank you. So, they can be of two types. Okay. One is directly usable, which means as is present in nature, you just modify, scrap, sharpen, do a little bit of work on it and you can use them directly, right. The other is something that needs processing. That means it is naturally available, but you can't use it as it's available in nature, you have to do something to it to improve its properties. So, there are two categories there, and of course, directly usable, some of the earliest materials that mankind used was stone and rock, and of course, that among those that needed processing, we used clay for instance, right. And so, roughly about 1.8 million years ago, I mean, so if archaeologists have dug up and figured out that implements of this kind that I've shown in the picture here have been dated back to about 1.8 million years ago. That means humans have begun to work with materials almost 1.8 million years ago, and these are mostly tools that are used for hunting. And you should remember those days humans primarily engaged in generation of food, and food was largely generated by hunting. So, they were hunter gatherers, and one of the things that set them aside, as Guru Prasad mentioned, is the fact that they could actually make these implements using naturally occurring materials, which made them a step ahead of the rest of the animal kingdom. So, you could sort of develop sharp tools with which you can do. So, what are the properties that these need to have in order to be effective? They need to be extremely hard, they need to be strong, they should not break when you are hunting. You shoot something and it breaks and you are finished. If the person is looking for a prey, if the other species is looking for a prey, and the other was longevity. That means you want these tools to last for a long time, right. So, these were probably some of the most important properties that were under consideration for those who developed these implements early. And of course, clay requires processing, which means you have to fire it. You can use clay, but unless you fire it, you will not be able to develop these kinds of things. And so, these date back to about 6500 BC, which means almost 8500 years ago, right. So, some of the earliest pottery that people have seen was these from various parts of the globe. And what are the properties that this material had? Formability, that means how easily can you shape them into various objects that you desire. Okay, so that was one. Of course, strength, longevity, and because these are containers, you need to be able to hold liquids without leaking, right. So, that is another property that you want. Porosity needs to be controlled. Since the focus of this talk is really on properties, I just want to highlight the properties that early humans would have been looking forward to having in these materials. Okay. And of course, thermal conductivity, that means if you are having something, you need to heat it up need to either you need to be able to conduct the heat through these containers. Okay, so that was probably some of the very early materials that have been developed using naturally occurring materials, both directly by making a little bit of change in the shape or by using processing methods. The second of course is wood. Wood was also much earlier. So, this is about 300,000 years ago. People have learned how to use wood, and wood, as you know, have different levels of hardness as they are procured. Some wood is relatively soft depending on the nature of the wood itself, and others are hard and much stronger. So, early years of utilization of wood would have actually gone through this. People would have gone through this selection process to identify wood that are strong, does not decay so soon, does not putrefy, and so the oil content in the wood would have been very important. You know, oil content in the wood and the density of wood is what distinguishes the hardness and processing properties and the strength of the wood itself. So, again workability and strength would have been the key properties that we are looking for, and of course glass, which is about 3000, which means 5000 plus years ago. And one of the properties apart from what you had in clay is that these were transparent, and there would have been a very important development in the eyes of people who first did it. That is to get some object that is not opaque but is transparent, while at the same time has many of the properties that clay did. So, these are a couple of examples of early materials that people had, and also it describes some of the properties that our forefathers would have actually been looking for in these materials. Okay. So, and then came the age of metals and alloys. These are clearly material that needs processing, right. Clearly materials that need processing is not used directly, and some of the earliest materials that have been used or metals that were used was copper. That is roughly 5000 BC, and then bronze, which is an alloy of copper and tin, which is about 3500 BC, and iron, which is more recent, which is about 1500 BC. So, these are the three main metallic materials, metal based materials that early humans actually learned to work with. And of course, what are the properties of these kinds of materials that you would be interested in? Copper is limited durability and was largely used for coinage, so coins and adornments. That means decorative parts to wear, okay, adornments. They were primarily used for that. Bronze, which is an alloy of copper, was much stronger, okay, and they were much harder and much stronger, and they were began to be used for weapons, okay. So, durability was one of the properties that were there, and hardness improved enormously. So, as I mentioned, bronze is of course a alloy of copper and tin. Alloying, the idea of mixing two metals, was one of the earliest forms of improving properties of metals, okay, and this gave a remarkable improvement, much more than what you would expect compositionally, okay. So, that means very small amounts of a second component can enormously improve the properties of metals, okay. This is something metallurgists and early man realized. And iron, of course, was the third one, which is the strongest of the three, and eventually replaced much of the earlier metals that were used by humans, okay. So, iron became the workhorse of most of the subsequent to iron's discovery. Iron strength made it among the best materials that you have, okay. And from iron, of course, steel, I will tell you the story of steel. The sharpness of swords and so on were clearly far better with iron. So, it was I would say the period between 12,000 BC and 600 BC is roughly believed to be, some region in that region was roughly believed to be the Iron Age. Okay, iron was a transformative material because it changed very many things, okay, just really made humans far more powerful and far more progressive than the rest of the species. I would say it was really a stage that demonstrated a dramatic difference of the importance of materials in human development. So, the key properties of iron that is hard, again that is mentioned earlier, is its strength, hardness and formability. By formability, which means I can shape it in various forms that I require. The early way of shaping metals actually was to soften the metal by heating it. That is, you make it a sponge iron, that is, get it very hot, and slightly porous, and then you hit it with a hammer or something that is hard to form it. Okay, so that was one of the earlier methods of making it. This is a good method, but you can't get fine tools. Fine tools with high levels of sharpness is not possible by this process of basically deforming materials at high temperature. That means you shape it when it softens a little. Okay, so finer tools were still and weapons were still not accessible, although for a lot of purposes that process worked. The most important development in handling metals was actually to be able to warm it up to temperatures where it became molten. Okay, and that came only when they realized how to get furnaces or how to get material hot enough to be able to melt metals. Okay, and that came in later. And here is a depiction by an artist showing early humans using smelting. You want to ask a question now?
I had a question. What's the difference between metal and alloy?
Okay, metal is a single element, like iron is one element. Alloy is a mixture of two elements. Okay, so if you have copper and tin, you get bronze. Okay, so copper is a pure element. In which class are you in? 5th. Okay, so you've studied. No, it's okay. It's all right. So element is a pure element. You know an element, what an element is? Yeah. So metals are pure elements and alloys are a mixture of two elements. Okay. Now I think it's okay to ask the question because you might not follow the talk otherwise. It's certain clarifications of terminology. Okay. So feel free to ask me questions. I would be happy to address them. Yeah. So casting was a process by which, as shown here in this depiction, this is molten metal. They have managed to melt metal, and here is a casting, basically a cast made out of clay. And what is done is this molten metal is poured into this cast and allowed to cool, like what you do with wax, right? So you take wax, you pour it into a mold, and you can shape it in any form you want. That's exactly what is done with metals, except that wax melts at 80 or 90 degrees typically. But this one melts at maybe 1000 plus degrees, right? So depending on the metal. So that molten metal is poured into this and then allowed to cool, and once it's cooled, you can take out the piece of object that he has. This is the casted piece of metal. This permitted people to develop tools which are far more well defined, sharper and so on, which really made a huge difference to the way human society developed subsequently. Okay, so here is an example from our own country. This is again an old one. This is the Iron Pillar of Delhi, and this is a remarkable alloy. It's an alloy of iron, primarily iron, but something that has lasted for so long. Its age is, it's believed to have been prepared or manufactured in roughly around 2000 years ago. Okay, less than 2000, but 300 to 400 AD, right? So roughly 1800 years, 17 to 1800 years ago. So this has lasted essentially without any surface corrosion, rusting, anything. Okay, so it's something that means societies both in India, China, and in the Middle East, Mesopotamia, people knew how to work with metals. Okay, and these were 1500 BC. People knew how to melt, work with metals, mix alloys, generate stronger metal based materials. Okay, so I think the other most important, more contemporary development that happened in materials is the discovery of steel. Okay, that is iron with a small amount of carbon. Okay, that means you add a little bit of carbon, improves its hardness and strength remarkably. Okay, and this was something that in most likely would have been a chance discovery, because the way they melted the alloy and isolated the pure element was by cooking it over coal. Okay, so coal is primarily carbon, and so what might have happened in the early stages is a little bit of carbon would have migrated into the molten steel, a molten iron, and generated a composition which is a mixture of steel and carbon, iron and carbon, okay, which was steel. And to their surprise, they would have found that the hardness of that they would have left it in all likelihood, as is conjectured by somebody who has written an article which I was reading, that they may have left that the molten iron and left it overnight over hot coal, and over a long period of time molten iron would have gradually taken up a little bit of the carbon from the coal, and to their surprise they would have found that the properties is far better. So when you find that, they were also scientists like today, except that they did not have the tools to investigate what was happening as we have today. But by experience, by looking at what would have happened, they would have conjectured that leaving the metal for longer times over coal actually improves the property. Go on.
What would happen if there was more carbon?
Yeah, it has an optimum level of carbon. You can change the properties of steel depending on how much carbon you have. Okay, stainless steel is another composition of metal, iron, which has both carbon and some other elements. So you can change the composition. These are complex phase diagrams. Phase diagrams means, meaning if you are looking at how property evolves as a function of composition, it doesn't necessarily simply constantly improve. Okay, it doesn't. Many of the properties go through a maximum. That means some amount is okay, but if you add more than that, it actually property goes down. Which means there's no, the natural way to think about it is, if I had a little carbon, it's getting better, so why don't I add more carbon, it'll keep getting better. That doesn't work always, okay, for a variety of reasons. So they would have, so early folks, fortunately they had the composition of carbon much less to get reasonably high quality steel, okay. So, alright, so here are some implements that were produced post discovery of the idea that you can have carbon doped into iron to give you a much stronger material, easily shapeable. And the most important things of these tools were that they could get these steel, when you discovered steel, you could get these and work them into much sharper and sharper implements. That means the efficacy of your weapon depends on how sharp it is. Okay, so if you have a blunt knife, you're not going to be as effective as if you have a sharp knife, clearly, right? So people who learned the technique of making steel and making weapons that are much sharper had an upper hand in the way they are handling their enemies. Okay, so think about societies in the earlier years. They were largely societies who were basically going around trying to capture more property, trying to get richer, trying to get more food. So they were hunting around, constantly moving from one region to another to find better. And if they, in their process of moving, if they encountered resistance, they will have to fight with them. And so those who had better implements would win the war, okay, would win the fight, and they would have more access to resources. So societies progressed by gaining access to resources, and the only way they gained access to resources was to constantly move and look for resources in neighboring areas and actually fight wars with those in the neighboring areas. So you can see it would have made a very important difference to early development of societies. So steel, mass scale production of steel had to wait a little longer, although blast furnaces that were not electric blast furnaces were existence, coal fired and other blast furnaces existed prior to this. Mass production of steel had to wait for the invention of electric power. Okay, so most of the electric arc furnaces required electricity, right? So this electricity happened little over 100, 110, 120 years ago. So it's not so old. When you think about the scale or time scale over which humans have lived, you realize that electricity, which is so fundamental to our living today, was discovered less than 150 years ago. It's so short when you think about time scales over which humans have lived. Okay, so this is much more recent. So discovery of electric arc furnaces. This is an example of an electric arc, photograph of an electric arc furnace. What you're seeing is basically molten steel, and as you know, when you heat metal, it gets red hot, and radiates light. Okay, so so that emission of light is what you're seeing with molten metal. It's being poured into a vat or something into which you either cool or you allow it to move into other regions. So some of the most important engineering progresses that were made was to develop techniques by which you can cast iron into shapes that you want and also convert molten iron into sheets. Okay, these were two important ideas that happened, and once we learned how to do this, massive expansion for infrastructure and transportation happened, which means steel began to be used quite, as you see it even today, it's used extensively for developing infrastructure and transportation. So here is an example of how molten steel is cast or it converted into sheets. These are rolls of sheets of molten steel which is made. I don't know if any of you have gone to an actual steel plant. I had the fortunate opportunity to visit a steel plant, and it's absolutely remarkable. The scale of a steel plant is something that you should see. You can still not go to a steel plant, young lad. You have to be at least 16, I think, before you can visit a steel plant. My son was less than 16 when I visited. He couldn't go, unfortunately, at that time. So, but it's absolutely something that all of you should visit if you haven't visited one. So here is what is done. So molten steel is actually poured into some kind of region which creates a flowing liquid like this, right, between rollers. And this flowing liquid goes and becomes a block. It continues to remain hot. You should remember the capacity to hold heat for a metal is very high. That means it doesn't cool so fast. Okay, it cools, it takes time to cool. So it continues to be molten, but it softens as it moves. It is cooling down and it is beginning to solidify, but still soft. As I told you, you can heated metals continue to be soft. So when it's soft, you can press them between rollers, and effectively, if you reduce the distance between adjacent rollers as you go forward, it will squeeze the metal to become thinner and thinner as you go towards the end of this. So by this point, the space between the two rollers are very thin, depending on what you want it, and so you get thin sheets of steel that continues to go through these rollers and finally piled up on a spool. Okay, and that's how you make this. And the importance of this is so high because you can hot press it, or you can even cold press it. You can shape it by simply taking the steel and pressing against some shape. Okay, so all your car panels and everything else is made by this process of using sheet. So you can imagine this is an extremely important product that based on steel. Okay, so likewise, you know, the railways. I have just one more point here to remember, that the development of railways, which is an important sort of societal facility that we have today, the development of railways was only possible because of the availability of steel. Remember, all the tracks, railway tracks across the world are using steel to make it, right? Steel is an important, you cannot use iron, it will rust. You have to use steel, okay? And the strength also. And the total length, I was just googling and checking, total length of railway tracks in the world is 1.4 million kilometers. Okay, that means you can wrap the world 35 times using the railway track that you have. You can wrap the entire earth 35 times around. Okay, so that's the length of railway tracks that are present today in the world. So you can see the implication of developing these remarkable materials like steel on human development in human societies. Okay, and of course, steel is an incredible construction material, and this is Eiffel Tower, which is nearly 200 years old. Okay, so this is made fully out of steel. So the fact that you can shape and form steel in whatever shape you want enabled us to build these beautiful things. This came later, and this is the most recent bird's nest, which was for the 2008 Olympics. Yes?
You said steel doesn't rust, so what's the difference between stainless steel and steel?
Stainless steel is, steel doesn't rust is not fully true. Steel rusts very slowly, okay, but it's very hard compared to pure iron, cast iron. Cast iron is more brittle, but steel is not brittle, okay, it's hard and it's tough. So that's the big difference. It is not completely resistant to rusting. If you look at the railway tracks on the side where the surface is not refreshed by the movement of wheels is rusted on the sides. Okay, but only the top surface is clean, and the top surface is clean only because there is the wheels of the train are constantly moving on it and abrading any possibility of rust that is happening. Okay, so if you leave a rail track unused, the top surface will also rust, okay, slowly. but stainless steel will not rust. Okay, yeah. All right. So this is the incredible thing that you can do with steel, right? You can construct this. Imagine the entire load. This is a fully steel bridge. That means all the load of the vehicles that are going there are borne by that steel. Okay, steel is primarily the structure that is giving you the strength of that, and these are the only 2 points at which it's contacted. So this entire thing is basically supported at the 2 ends with the help of those cables, of course, that is running on top of this, that is holding it, right. So it's a cable bridge, suspended bridge. Okay, so now let's just take a pause here. So much of the early focus of material development was primarily on mechanical properties. As of now, I have only discussed properties of materials that rely on strength, that gives you strength, formability and durability, right. So strength, hardness and formability were the 3 main parameters of properties of materials that people sought at those times. And what were they making with it? They were making weapons, agricultural implements, of course, that is to dig soil, to agrarian society is clearly formed by then, and construction material and transportation. So this is all what they were using, and for that most of those properties, that is strength, hardness and formability, was adequate to address these for most of the properties that were required. Okay, with the discovery of electricity and power generation was clearly a turning point in the evolution of materials. The search for new materials with new properties accelerated rapidly once we had electricity. Okay, so you can make a connection between electricity and rapid transformation of material science. So incredible development of novel materials soon followed, right. So we'll see what it is. Okay, so young man, this is called the periodic table. You know, okay, good. So this is an arrangement that Mendeleev figured out by doing some very preliminary experiments about elements. Okay, so all these elements are arranged based on certain properties of these elements. I won't go into the details of it. Okay, it basically is the number of electrons that are present in the valence shell. So okay, so now, so all materials are made up of elements. Okay, that's fundamentally it. That means you combine elements in different ways and you will get different kinds of materials. So that basically was understood, okay, today. Aluminum, I didn't say much about it. Aluminum is a relatively young material of remarkable strength, and all I'm going to say about aluminum is this: it's a really a remarkable material with outstanding strength to weight ratio. It turns out that aluminum as an element, as a metal, is far less dense. That means weight per unit volume. Okay, that's density. It means you take 2 cubes, each cube of, let's say, 5 centimeters by 5 centimeters by 5 centimeters, you will see that iron is much heavier than that of aluminum. Okay, and therefore if you measure the strength, normalize it, which means you say strength per unit mass, how strong is it with respect to its weight, then aluminum does exceedingly well. Okay, and that's one of its strengths. And of course, as in iron, if you add small amounts of other elements and you make an alloy, the strength, the hardness of aluminum improves dramatically. Indalium is one example. Okay, so easy to develop alloys with other elements that improve the material strength without changing the density very much. Okay, and that was important. That means you could quickly develop alloys of aluminum which had very high strength but continue to remain light, and that's one of the reasons why aluminum is a remarkable material. And today, if we did not have aluminum, I suspect that air travel would have been far more difficult. That means most of the chassis of the aircraft is actually continues to be aluminum today, but very soon we may have organic composites replacing aluminum. Okay, so that is about all that I have to say. All I want you to remember is aluminum mass production began only about 150 years ago. Was discovered 150 years ago. Mass production happened only after the discovery of electricity. Okay, because aluminum is manufactured by an electrolytic process today, okay, which needs electricity. Okay, so so physical origins. So so far humans have been just working with materials, developing materials by trial and error. They do something, they figure out it works, do something a little more, see how it works and so on. No in-depth understanding of what the origins of this physical properties are. Okay, so people in the last 150 years, people began to ask these questions. What makes a material strong? What makes it a thermal insulator or a conductor? Okay, what is the physical origin of this? What makes something conduct electricity very well, something not conduct electricity very well? So what are the fundamental reasons? And little over a century ago, this is just little over 100 years ago, fundamental developments in physics and chemistry and engineering sciences actually helped us answer these questions. We began to understand primarily fundamental physics and fundamental chemistry began to reveal, we began to understand what are the origins of these wonderful properties of materials. And once we began to understand the origins, we were able to manipulate materials far more cleverly. Okay, and this really rapidly increased the development of materials that became accessible to us. So I would say this is at the core of the rise of material science that happened in the last 100 years. Okay, so again, so this is the periodic table. I want to remind you that all materials are made up of a mix of these elements. Okay, mix means different things. So so far we were primarily dealing with metals like this: iron, a chromium, bit of chromium, and zinc, lead, copper, zinc, and so on, right? So we were only dealing with these, and aluminum here, of course. Okay, so we were dealing with these elements. Now, the 20th century, which is the 1900s, okay, that is till we came to the 21st century, the 20th century elements. So what are the elements of the 20th century, if you were to ask me? I would say these were the elements. Okay, the primarily boron, carbon, nitrogen, aluminum, silicon, phosphorus, gallium, arsenic, indium, tin as well. Okay, so these are primarily. So the focus shifted from these elements, from iron, copper, zinc, tin, and so on, to these elements. Okay, these elements becomes a focus of the last 1900s. That means the last 100 years. So I'll say a little bit about silicon, because silicon is probably one of the most important elements today in the context of our life. Okay, clearly one of the most important elements. So silicon is just below carbon. For those of you who know a little bit of chemistry, you see silicon is just has the same number of valence electrons as carbon. Okay, it follows in the same group. So it just has one more shell. So it has properties similar. Some aspects of silicon behavior is similar to carbon, but most of the others are very, very different. Okay, so it turns out that silicon is a semiconductor, which means it doesn't conduct electricity very well, but it's also not an insulator. It lies somewhere in between. So you can heat it up and it will conduct electricity. Okay, that means you can get conductivity to happen when you heat it up. But what people figured out very quickly is that, again, just like alloys, when you mix one element with the other, here of course you needed to understand the fundamental chemistry and physics of these materials. So what you should remember is anything left of silicon has one electron less in its valence shell. Anything to the right of silicon has one electron excess compared to silicon, right? So if this has 4 valence electrons, this has 3 valence electrons, and this has 5 valence electrons. So people figured out that if you dope, it's called doping now, it's not alloying, but the idea is similar. That means you put a little bit of this element or boron or aluminum or gallium, any one of these, you put it in silicon. The size of silicon and these atoms are not very different, so they actually fit fairly well in the organized structure of silicon. But at the same time, it has one less electron. Okay? And as a result, you have a hole. When you don't have an electron, you call it a hole. That means a gap, a species which should have had an electron, doesn't have an electron. Okay. But if you add these elements to silicon, then it has one extra electron. So which means it has an electron in excess, and that electron is actually movable. Okay. Like the holes, it turns out that if you have a hole, the holes are not stationary, even though the element which you doped is at some single point in the entire lattice. Okay, so like a classroom is like I mean, what of you are sitting is like a lattice. If you have a chair that is next to you which doesn't have somebody, and somebody comes and sits down with an extra electron, the extra electron doesn't sit there, it actually is able to move in the entire object. Okay, so that's what is important. So likewise the hole also is able to move in the entire object, and this creates a very interesting situation, which means the conductivity of a doped silicon actually becomes far superior, and it's easier to excite them using small amounts of heat or light. Okay, that's fundamentally the idea. So what happens is that's what I've written here, right? So you have extra one less valence electron or one more valence electron, and then you develop two types. If you have an extra valence electron, you have an n-type semiconductor, which means electrons are the species that are moving. If you have one less electron, then you have a p-type semiconductor, which means the holes are moving. Okay, so that's fundamentally how people develop solid state physics of and it turns out that if you take a material that has excess electrons and you take another material, another species that has excess holes, and you put them in contact, then you create a very interesting species called a p-n junction. Okay, and it turns out that a junction like this has very interesting properties. Okay, electrical properties. So this is a p-n junction. So this is called a p-n diode. So this is a p-type semiconductor and this is an n-type semiconductor, and you apply a potential. I told you generation of electricity and discovery of electricity was key to development of materials subsequent to that. Okay, so here is an example. So which means if you have a p-type and you apply a negative bias, that means this is positively charged but you connect it to the negative electrode, and this is negatively charged and you connect to the positive electrode, then you have a bias, you are pushing the electrons the wrong way. Okay, so that's called a reverse bias. But if you put it the other way, it's a forward bias, and it turns out that a diode like this is a one-way current valve. So it's like a valve, that you have. That means it will allow fluid, there are non-return valves called NRVs. I'll complete the sentence. There are valves which allow liquid to flow one way, but it will not allow it to another way. The valve in your heart is a one-way valve. Okay, that means it's a flap that is there, it allows blood to flow this way, but blood from here cannot flow back down, right? So it's a one-way valve. So diode is like a one-way valve. It allows current to flow in one direction, but does not allow current to flow in the opposite direction. Yeah, go ahead. Okay, I think you're too young for you to understand that. That means in the negative, when it is negatively biased, it is not completely zero. The current is not completely zero. It leaks because of the fact that, everything has a little bit of energy at a particular temperature. Okay, and that's called the thermal energy. And the thermal energy is enough to push a few electrons in the wrong direction. And that's what happens. So which means if you cool it down, the leakage current will go down. Okay, so leakage current is a current that happens as a result of a little bit of energy. So thermal energy means everything has some energy at any temperature. The amount of energy available to anyone at any temperature keeps going down as you reduce the temperature. Okay, and that's basically it. Okay, so in other words, it allows. So it is, and so the important point is in the forward direction, it suddenly exponentially rises. That means the current, it's almost like a switch. It just allows the current to flow very much as you apply a forward bias, a small bias. So what it does, one of the important sort of ramifications of this is that when you have a AC current, which means the voltage actually goes up and down, right? It's an alternating voltage. Because you don't move in the negative voltage, it turns out that you can rectify it. That means you take an AC current, an alternating current, and you can convert it to a constant voltage current. Okay, that's a DC current. So that's one of the interesting ideas. But more than a diode, the most important discovery that happened was this called PNP junction. Instead of just a diode, if you have a P type semiconductor, N type, another P type, and you make a sandwich, then you get a transistor, or you can have an NPN. Okay, so PNP or NPN. So what this does is quite interesting. Firstly, it can amplify the current. It can act as a switch. That means it can either, depending on the controls that you have, depending on the voltage that you apply, it can either allow the current to go through or stop the current. Okay, so it's a switch, and this is fundamentally the basic element of everything, all gadgets that we use today. Okay, so every gadget, electronic gadget that we use today will have transistors, not one, but hundreds or thousands or millions even. Okay, so your computers will have million transistors. So these are basically a huge network of things that will either allow or disallow, and by that process of allowing or disallowing, you are creating a complex circuitry that allows you to do many calculations and many other things. It can power regulate, it can current control, and can do a lot of things. This was discovered, imagine, this was discovered just in 1947 when we got our independence. So it's really just over 75 years old. So very new. And this is probably one of the most important discoveries that mankind has made, okay, because it transformed the ways in which we live at remarkable levels. Okay, so it's the heart of all computing devices, your cell phones, everything. And of course, instead of a typical transistor, there's a slight development. I won't go into the detail. It's called the field effect transistor. That is what is today used. A field effect transistor simply applies a small voltage that controls the current that is going through two other leads. Okay, you apply a voltage to the gate and then you control the amount of current that goes. And MOSFET is one example of an FET, that is metal oxide semiconductor. And all integrated circuits, which you call ICs and microprocessors, use numerous amounts of transistors in combination with various other elements, circuit elements. Okay, and Bardeen, Brittain, and Shockley were awarded the Nobel Prize for the discovery of the transistor. Okay, so light and semiconductors. Now let's see. So we have talked about current transmitting ability, current conducting ability, devices that use materials to control current, okay, as a function of voltage, and that turns out to be important. What about light and semiconductors? So this is another property called electroluminescence. How am I doing with time? Can I take another 15 minutes? Please. Okay. We started at 4:15, I think. So electroluminescence is another interesting property where you apply a voltage and the material gives out light. Okay, that's what luminescence means, something that gives out light. Electro means you apply a potential and it gives out light. Okay, so that is, and photovoltaics is the opposite of electroluminescence. In other words, if you shine light, it will develop a potential. Okay, that means you can use solar energy to do work. That means you develop a potential and you run some load from the two leads of the potential, you can do work. Okay, so that means that is the idea of photoluminescence. So in some sense, electroluminescence and photovoltaics are the opposite process. One of them, you apply potential, it gives out light. The other one, you shine light, it gives you potential. Okay, so it's, in a rough sense, it's the exact opposite property. But the materials that do these are completely complementary. Those that electroluminescence typically will not be good photovoltaics, and those that are good photovoltaics will not be good electroluminescent materials. That has a fundamental relation to the property itself. But both of them are in the same class of materials, okay, but slightly different, subtle differences between the two. And all of this became possible only because you understood the fundamental physics and chemistry of these structures. Okay, that was very important. And the construction of devices required the ingenious engineers to be working with the fundamental scientists. So here is a light emitting diode, and this is something that all of you are seeing using all the time. Diwali just went through recently, and all of you would have used this in your houses, right? All the lights that you're using today are all LEDs, okay? They're all light emitting diodes. And you can get various colors depending on what color you want. You can use different semiconductors one way. The other is to simply have different dyed composites around a white light. So if you have a white light and you cover it with something that is like a red filter, then you get a red light. Yes, tell me, young man. Okay. So you wait till I complete and then you might not have a question, right? So the point is you can do it many ways. You can change the semiconductor itself to get different colors, or you can use something that gives you white light, okay, which is composite light, and then you cover it with something that has a filter. Like this might have a red colored dye in this transparent matrix, okay, so it will give you red light. So it's almost as if you're wearing glasses. Okay, so the basic idea is, again, you can see that this is again a diode, so that means you have a p-n junction. And without going into the details, what you want to remember is that by applying a potential, you can push electrons into what is called a conduction band. Okay, so when you have materials like metals or semiconductors, you develop bands. Okay, that means you have regions. If this is energy, you have regions where there are electrons and regions which are empty. And so there is a gap that you create between the regions that carry the electrons and the regions that carry no electrons. That means they're empty. And so much of the properties that you get is by pushing electrons from the region which has electrons to the region which doesn't have electrons. And once they are there, they don't have neighbors, so they are free to move around. Okay, here it's very crowded. Down there it's very crowded, and so you can't move. It's like a crowded bus. But once you go to the roof of the bus, there's nobody there, you can run around, right? So that's exactly how the conduction and valence band happen. The valence band has full of electrons. They are not easily mobile. Very often you jump here and there are less electrons and they move around very quickly. So what you do here is you push electrons to the conduction band and you create holes. That means you remove electrons from the valence band here, and you can cause these two to combine to give you light, and that's what an electroluminescent process is. Okay, that means you apply a potential, you generate electrons and holes, and when these electrons and holes combine, it gives you light. Okay, that's a very simplistic statement, but that's basically what it is. And you can see that the elements that are used is an example of this. I'll show you so you see here, this is an example of an LED material, that is indium gallium nitride. Okay, so that means it's a combination of elements that belong to the 20th century elements that I mentioned. Okay, now light and glass. Okay, so this is another very interesting discovery that won the Nobel Prize more recently. Should have been one long time ago, but the discovery of glass that has using glass to make optical fibers. Okay, this is probably another extremely important discovery of this last 50 years. Okay, so many of you young kids, you know total internal reflection from mirage. You would have studied mirage in your high school. That means if you're in a desert, extremely hot roads, why do you have to go to a desert? In summer here, if you have these nice tarred roads, you will actually see reflection of the tree on the road at a distance, right? And that is created by total internal reflection. Okay, and here of course what happens in a hot day is you create a gradient of air. The density of air is different. Very close to the surface of a hot road, the density of air is less. As you go up, the density becomes higher. So you create a refractive index variation. Okay, refractive index, just to remind you, is basically the relative speeds of light in that material compared to that in vacuum. Okay, so it's a property related to interaction of light with material. Okay, so when you have something of high refractive index cladded, this is a two-dimensional figure. So it's basically a fiber, a very thin. All of you would have seen optical fibers. I have a photograph of that here. So this is an optical fiber that can transmit light through this fiber. So there's no light coming out anywhere here except at the end. Okay, so that means light will go through this fiber. The fiber can bend any which way, but still light will go through and come. This is an extremely important discovery, and for those of you who had laparoscopy done, that means you have things put into your body and people can see images of what is happening. At least the first generation ones carried light through optical fibers. Okay, come in. But yes.
So here we can see it's happening as total internal reflection, and you said that no light is coming up.
Light is coming out only at the end.
Right.
Yeah, end it will come out because.
How can we see that light is going inside? How are those wires being?
Oh, then that's not. Well, that is a little bit of light. You're correct. Okay, that means there's a small amount of leakage everywhere. It is not 100%. Nothing is 100%. Okay, when it's total internal reflection, it doesn't mean no light is leaking out. Okay, extremely small amounts of photons will leak out. That's why the intensity of light is packets of energy, right? You remember photons, one second. So if number of photons that come out will always be smaller than the number you sent in, because there is finite but extremely small amount of photons that are leaked out. So the point is, over long distances you have to amplify it again. So that's why you have at sections you will have amplifiers that increases it again. Go ahead. Few microns. Okay, 1 micron is about 1,000th of a millimeter. Okay, so it will be maybe 100, 150, 200 micron. So you might say 1/100th of a millimeter. Okay, you take a millimeter on a scale and imagine you divide it into 100 parts, and that's no 10 parts. I said 100 microns. So about 10 parts. So 1/10th of a millimeter. Okay. All right. So when you do that, when you have a cladding that has a lower refractive index, that means a coating around the glass fiber that has a lower refractive index than the glass fiber itself, you can then generate total internal reflection, and by doing so you can cause the light to pass through the fiber. Okay, and the beauty of this is that it's not sensitive to twists and turns. You can make a knot and still the light will go through it. Okay, that's what is important. So it's faster, lower interference. Unlike passing current, it's of course much faster because it travels at the speed of light. Okay, and electrons don't travel that fast. Okay, so compared to conduction of electron, which is electricity, transmitting information using light is much faster. Okay, and that's why they use optical fiber. And of course, it is not sensitive to interferences. That means you have electromagnetic radiations around, it doesn't bother light going through it. Okay, but if it's current, it is influenced by electromagnetic radiation around. So here is another small statistic. So this is how the world is connected with optical fibers. So there are these huge optical fibers that go underneath the sea and connect, for instance, the American east coast of the US, United States, to Europe. Okay, so this is an underground light transmitting cable that goes below the sea, and it's huge distances that it goes, right? So the total length of optical fiber cables that run below the ocean is roughly 5 billion. 1 billion is 10 to the 9, okay, 10 to the power of 9. That means 5 followed by 9 zeros. That is the total length of optical fiber cables that is going below the sea. Yes? Under the sea, yeah, under the sea. If it's flowing over in the bed, all the way in the bed, because you don't want any ships or anything to disrupt it, right? So you go all the way in the bed, okay? And still there are problems, there are breakages that happen in these, and people have to get down there and repair it. So can you believe how hard it is to maintain these fibers, optical fiber cabling along the sea? And this is at the heart of our connectivity, the global connectivity. So when you hit something, you're searching and it's going and looking for information in the US or somewhere else, you're utilizing these fibers, optical fibers, to almost immediately get information back, right? So it's extremely rapid. Okay, now let's move on to, I'm going to have to finish soon. So carbon in its form. So now let's come to the next element. So carbon, okay, this is the element that I'm talking about. And of course, carbon has received suddenly a lot of attention in the last 30 years. There are various new forms of carbon that have been discovered. One is the famous buckyball that looks exactly like your football, okay, having 5-membered cyclic rings and 6-membered cyclic rings, exactly like the way the football is. And that's the only way it turns out you can construct a sphere with geometrical shapes like pentagons and hexagons. Okay, so this is a beautiful shape that automatically happens with carbon, which was discovered a little over 25 years ago. Okay, the other is of course graphene. All of us know graphite. If you have used pencil, you're using graphite every day. And the reason why pencil works, you know why pencil works? Sorry? I know, but why are you able to write on a paper with a pencil? Friction is all right, but can you use any other material to? You're correct, exactly. So the point is graphite itself is a layered solid, and the interaction between layers are not very strong. So when you rub graphite on a rough surface like paper, it transfers one layer of that graphene, effectively graphene sheets, a few layers of graphene onto the paper. Okay, it's a soft material that is layered, allows you to transfer that onto the substrate. Okay, so that's graphene. So what happened was, the man actually did a simple experiment. The person who won the Nobel Prize did a very simple experiment by just using a scotch tape, putting on a graphite piece and peeling it out. The top layer stuck and a few layers come on to the graphene. And the imagination of this individual obviously, but we were doing it all the time, transferring few layers, it's not a single layer. But it turns out that if you are able to separate a single layer of graphene, the properties of this are quite remarkable. Okay, that's what they showed. And of course, carbon nanotubes are a version of this. You can, if you take this single sheet and wrap it up, you can wrap it up in different ways. You can make these kinds of tube. You don't physically wrap it up. It happens as a wrapped up. So the process of manufacturing or making it gives you either, when you try to make various forms of graphite or carbon based materials, you would generate both single walled and multi walled tubes. These are concentric tubes of different dimensions that are inside one another. Okay, these are very interesting material again because of its unique properties, especially electrical conductivity and barrier properties and so on. Okay, now organic materials, right? So the next thing is, so I said carbon and organic materials, and now let me come to organic materials. So what is organic materials? Organic materials are basically a combination, largely, okay, few outside of this, but largely carbon combines with nitrogen, phosphorus, oxygen, sulfur and hydrogen. Okay, most of organic materials have these elements. Okay, it doesn't mean it doesn't have this, it can have halogens, it can have a few other elements, but largely it is these 5 plus 1, 6 and a few halogens, and that makes all of organic chemistry. Okay, all of organic molecules are built up largely based on these. Okay, a few others, as I said. Okay, so what are the organic materials that are of interest in the context of materials itself? Okay, it turns out there are three important things that I'd like to focus on based on organic materials. One is liquid crystals, the other is luminescent materials, much like you have semiconductors that emit light when you apply electricity. There are also organic entities, organic materials that do the same. They emit light when you apply a potential. Okay, and those of you who have heard the term OLEDs, OLEDs or MOLEDs, etc. OLEDs refers to organic LEDs. Okay, so that means these are LEDs built out of organic material. Okay, it turns out that chemists have a way to change the color very easily for organic LEDs, and that's why it's become important. And those are luminescent materials, and the third, of course, is polymers. That's the area in which my research is. So I talked to you about these three, and then I'll close. So liquid crystals are very interesting molecules. Okay, it's yesterday's display technology. It's gone today, pretty much. Okay, it turns out that if you take molecules, these are molecules. These are built out of carbon and hydrogen primarily. There's no other element in this, only carbon and hydrogen. Okay, so it's a combination of carbon and hydrogen. Unlike alloys, which you don't have a shape, when you combine carbon with other elements, you actually make small molecular entities. That means they are like benzene or sugar. Sugar is a molecule, right? So like that. So these are organic molecules that have a long shape. Okay, and the idea is that that's why I have this representation of a molecule. It's an elongated object. Can I get some water? This bottle is fine. So these are elongated objects. When you have elongated objects, they will pack like this. Okay, then in the solid state, if you have spheres, you can pack them very effectively. Like oranges, when you go to the fruit shop, you can see how it's packed, right? Beautifully. those are hexagonally close packed. They know that how it's stable, they arrange it, and then between the gaps they put the next orange, and they are very stable. And atoms actually in the solid state organize much like how Malleshwaram or wherever the market is, they organize fruits, okay, much like that. But you have long objects like this, you can't arrange them like that. And it turns out that the shape, because of the anisotropy, when I say anisotropy, that means when I go from the center of a sphere to any point on the surface, the distance is the same, right? That's the definition of a sphere. From the center I can go to the surface and the distance will be the same. But in an object that has a shape like this, from the center the distance of different points on the surface is very different. That means the shape is anisotropic. It means it's not spherically symmetric. The shape is not. And we have shapes like this. It turns out that they will organize in the solid state in this fashion. Just an example. And because they organize like this, the way in which molecules interact along the length is very different from the way they interact. That means the interaction between these two are sticking to each other stronger compared to the sticking between these two, because these are pointed regions of molecule in this representation. They don't interact very well like this, but they are interacting very strongly like this. So that means because of the difference and because of this anisotropy in shape, they also interact anisotropically. Okay, that means the strength of interaction between the plane, that means the molecules are interacting along this plane stronger than one plane is interacting with the other. As a result, when you supply heat, it doesn't melt directly into a liquid, but it goes into an ordered liquid, and that is called a liquid crystal. All these are representations of a liquid which continues to retain some element of order. Okay? And that's why it's called the third state of matter. That means it's neither a solid nor a liquid, it's something in between. Okay? And it's called a mesophase. That means a phase that exists between the solid and the liquid phase. And those phases can have different kinds of arrangements of the molecules itself. Okay? So don't worry about that. But it turns out what is most important is that because this is a liquid, you can shear it. That means it's not like a solid that you can't move around. You know, take it between two plates, you can make the plate slip because the liquid moves. So you can make it move. And so what a liquid crystal display does is it utilizes the ability of this to move. Okay? So suppose I have two plates, conducting plates, which are transparent, let's say, and also these molecules have what are called dipoles. That means there is a positive end and a negative end in the molecule. Okay, it's constructed to have a dipole. And when you have a positive end and a negative end, and you apply an electric potential, then these molecules will tend to align so that the positive end is near the negative electrode and the negative end is near the positive electrode. That means these dipoles will interact with an electric field to orient. Tell me. No, I am not going to explain that. It's a little hard. These are different states of order. Okay, that means the molecules in the liquid state can have different types of ordering. Okay, a pneumatic is one of those orders. Okay, imagine that I have sticks, long sticks, and all I can say about it is that the sticks are all in the same direction. Okay, that's a pneumatic liquid. Okay, no other order, but the sticks are in the same direction. Okay, that's called a pneumatic. But you can also arrange the sticks like this. That means one stick and bunch of sticks in one layer, bunch of sticks in another layer. These are called smectic. That means they are layered. Okay, but if they are not layered, it's called a pneumatic liquid. Okay, that means the centers of these, if I were to disappear this and make marks on the center of each of these objects, then the center will be random. The centers will be random, and that's a pneumatic liquid. But if I were to put dots on the centers of these, then the centers of these will lie in roughly in one plane, and that's called a smectic. Okay, that's a subtle difference. I didn't follow. What is that? This one. Why are there lines means I didn't. Oh, yeah, you come to my office sometime, I'll discuss, because these is basic, the way the chemists love to draw structures like this. Okay, they draw lines to each of these point here is a carbon. Okay, These are carbons, and if they are forming a bond, a chemical bond, you draw a line to connect the carbons. Okay? And for simplicity, the hydrogens that are present here is not written. So, it is just a manner in which you write, okay, the chemistry. Okay. Alright. So, the beauty is that if you apply a field, this is an electric field, you will tend to orient these things in the direction of the field. That is fundamentally what is the principle of a display. So, I am going to just tell you how an LCD, a liquid crystal display works very quickly, because I think I am running out of time. Okay, so, the thing is that light has different kinds of characteristics. Okay. So, I am not again going to go into detail because of materials talk. Light, light is basically a wave that is moving, okay, and it has certain characteristics. And when a wave moves, it is the amplitude that is changing as a function of time, okay, or position. And so, you can have the wave, a typical light is moving like this, but this wave is actually undergoing change in the direction of the amplitude. Okay. So, that is what is apolarized light. But you can do something to light so that the polarization, that means the amplitude variation is only in one plane, okay, and that is called a plane polarized light. Okay. So, what is done in a nematic liquid crystal is to use a polarizer to polarize the plane. Okay. So, and it turns out there is an important thing that I forgot to mention. Okay. The important thing is, these molecules can be made to orient in different directions on a substrate by an extremely simple, almost unimaginably simple technique of simply rubbing the surface. That means if I take a surface, I have a certain kind of coating and I simply rub it in one direction, okay, for some time. Then if I put these elongated molecules, their molecules will align themselves in the direction of the rub. Okay, that is a almost surprisingly simple technique to align molecules. Okay. So, so if I want molecules to align in this direction, I simply rub this plate. This is a plate, I rub it like this with some object which creates certain wells. Basically, you create small wells that are in that direction. So, molecules go and sit in those wells. Okay. So, that is what you do. So, it turns out that you can orient. So, if I have a plate like this that is rubbed in this direction, so that molecules in this plate are like that, and here I have a plate that is rubbed in this direction, so molecules in this is like this. So, basically I have one plate where the molecules are along my long fingers, and in this plate the molecules are in this direction. Okay. That means there is a 90-degree difference between the angles of this plate and this plate. And what is really remarkable is, if I put a liquid crystal, that is, let us say a nematic liquid crystal like this, okay, like this, in between these two plates, the molecules at this end will be oriented like this, and the molecules at this end is oriented like this. And even in a gap of, let us say 100 to 200 microns, the molecules will be oriented here and it will be oriented here, and in between they will undergo a twist, because in between it has to be in this, it is this direction, molecules are like this. So, by the time it gets from here to here, the molecule will have to gradually turn in this direction, and it turns out that molecules are oriented like this, okay, when you do that. Now, that is the starting point. Okay. Now, what you do is you apply a potential. So, if you apply a potential, the molecules will want to orient like this, and that changes it. So, let us say I have light that is polarized like this entering in the same direction as the molecule polarization, and it turns out if I have this is called a twisted nematic display, the molecule will, the light also that is going with the plane in this direction will gradually twist and become vertically polarized by the time it gets out. So, that means if you have one of these liquid crystal display which has rubbed in like this and like this, I send light like this, and by the time it comes out it will be twisted by 90 degrees. So, if I have a polarizer with the lines in this direction and a polarizer with the lines in this direction, the light will go through because the light has undergone a twist in the polarization and it will exit from here very easily. Okay. That means the entire display is transparent now to the light with this configuration. But as soon as I apply a potential, the molecules orient like this and it loses that control. The light no longer turns by 90 degrees, and so it will become opaque. So, a liquid crystal display is a display that works on the principle of allowing light to move through the display or turning it off. So that means light can either go through it or not go through it, okay, and that's the fundamental principle of a display. I don't think many of the young people would have seen a liquid crystal display, but the point is that either the background is dark, which means you will see, if it is going through, you will see a dark background, which is a display is there, otherwise you will not see it, okay. So I'll have to quickly go through. So okay, so luminescent materials, just like just like gallium, indium gallium phosphide or indium gallium nitride, there are many organic molecules. What is fundamentally common to that is everything has these double bonds, okay. So they have what is called conjugated. So these are molecules that exhibit these light emission, and I'm not going to go into the detail, but the idea is that you can cause excitation. I told you that, no, I don't think I'll have time, but the thing is, organic materials can give you, by depending on which structure you choose here, these are all different molecules, they can give you different color of light, okay, and that's fundamentally the breakthrough that organic fellows like, because making different types of molecules is what they are good at. Chemists can easily make these molecules, and it turns out that you add bits and pieces of fragments and you can change the color very effectively, okay. So that's basically it, and this is very much similar to the other light emitting diode. So you can this is called the lowest unoccupied molecular orbital, and you can inject holes and electrons in this too, and they combine in this emissive layer to give out light, okay, and this will be a transparent anode and this will be a cathode, okay. So that's basically how light emission works, okay. So I want to just switch because it's today is the, so if you ask me what is this century, which is the element that is more important, that is the 21st century, I think lithium is probably qualifies as being one of the most important elements as of now. It may become sodium very soon. If it does, all of us will be happy because sodium is available in plenty, lithium is not, okay. So I'm going back to this. Lithium is an extremely light element. It has an atomic number of 3, which means 3 electrons only, very light and therefore very effective. See, one of the key aspects of a battery, this is used primarily in a battery, okay, lithium batteries, all of you would have heard. One of the key factors in a battery is how much is the energy that it can store per unit mass, okay. It's called the energy density. It means how much energy per unit mass, and the lighter the element that you use in the battery, the mass is lesser, and so you can store more energy per unit mass, and that's why lithium is so important, apart from the fact that it's easy to oxidize, okay. So but light element is important. So how does a battery, so which means you can have rechargeable lithium batteries, you can have supercapacitors. One of the problems with a battery, traditional battery, is the rate at which you can draw energy from it is not very high, and all of you want cars that can accelerate from 0 to 60 in 5 seconds, okay. So if you have a lithium battery, you can press how much ever you want, it will only go slowly because you can't extract energy out from the battery very fast. And so what is done is, it is done in conjunction with something called supercapacitors. The subtle difference between battery and supercapacitors is that capacitor, as a definition you know, many of you know, is that you simply polarize within a dielectric medium, you pull electrons to one side and holes to the other, okay, and you just hold it. Because the medium is not conducting, it's a dielectric, they stay like that and gradually move back. So it's basically you're forcing a separation of electrons and holes, and you allow. That happens very fast. In a battery, you actually cause a chemical reaction to happen. So you store energy in a chemical reaction. In a supercapacitor, you store energy by just pulling electrons and holes apart. And this one can discharge very quickly, extremely rapidly. So this supports, when you want to accelerate from 0 to 60 in 5 seconds, this one will back up. So in conjunction with the battery, the battery stores more energy. This can give you energy much more quickly, okay. So that's why it is used in conjunction with this. Okay, so this is rechargeable battery. I would not go into the details, but the idea is that lithium actually is in the plus, Li plus here, and it becomes lithium elemental, it's Li plus here and becomes lithium element here, okay. So that's basically it. And so in a sense, a battery is doing this, okay. This is the parallel I'd like to draw. When one is charging the battery, it's like taking water uphill, okay. So you take water uphill, you have to do work to carry it up the hill, and you let the water go it will flow automatically down, right. So, battery is exactly like that. So, it is like taking water up the hill and storing it up. So, it has potential energy, and as it comes down it can do work, and that is how hydroelectric power plants work, right. Water comes down with high velocity from the hill, and you can allow it to drive a turbine and you generate electricity. So, it is doing work. Okay. So, exactly like that, you push in a battery, you push it uphill, you are pushing it uphill, and when you let go, the electrons are simply cascading down, and as it cascades down, it can do work exactly like water flowing from the hill. Okay. So, it can do work, and that is exactly what is a battery. Okay. I am going to stop. This is the last material that I would like to talk about, and more often than not, people will have more questions about this because it is high up in their mind. So, sometime in the early 1900s is when the idea of molecules, not necessarily very small molecules, but extremely large molecules became an idea that was accepted about 100 years ago. Okay. Prior to that we were accepting it, but remember, all of us have very large macromolecules in our body, DNA, proteins, all of them are polymers. Okay. So, they are all polymers, but a special type of polymer. So, these are synthetic polymers. I say a necessary evil because I do not think we can live today without plastics, polymers, but it is also evil, as you all know. It has problems. It is not evil, we are evil, we do not know how to handle it. The point is there are a variety of polymers, and these are the objects that are made with polymers, right. All of these you have seen. I am glad that what they gave me was in a glass bottle. Okay. So, but the lid is polymer still. So, okay. So, these are quintessential molecular materials. I am not going to go into the detail because it is a little hard, okay, to for me, given the time. I am almost completed, but these are basically very long molecules. Okay. So, I have just this to say, and it is the size that makes a difference. So, what is unique about polymers is that it is extremely lightweight, very high strength and easy processability. Okay. That is the key, and it has certain unique behavior like rubber, viscoelasticity, adhesive properties, gels, fiber formation. So, it can do so many things that are very unique, and what is nice is you can do this processing at much lower temperatures. Okay. So, you have very long chain molecules, and when you stretch it out, it can be as long as 1 micron, but it will be usually in this kind of what you call random coil shape. Okay. And so the size is much smaller when it becomes bundled up. Okay. So, okay. So, I will skip this. Okay. So, I will just end. Before I end, I just want to tell you why polymers are unique. A rubber band is an interesting object, right. It is a remarkable object, and the behavior of a rubber band is uniquely polymeric. There is no other material that can give you such long elongation and go back to its original state. There is no other material. Okay. So, this is a unique property of polymers, of long macromolecules, and why it is so unique is because the polymer itself is actually unwinding. It is all wrapped up like this, and when you are stretching it, the polymer is stretching out without breaking. It is becoming long, and when you let go, it actually likes to go back to that shape. Okay. And that is driven by a property called entropy. Okay. So, I will not worry about that, but when you pull these things, objects, they will usually change. If you take polyethylene and pull, it will pull, but it will not go back. Okay. And that is because it is not connected. Okay. So, they all need to be connected to go back. So, what is done is something called cross linking. That means you actually tie up each of these at some points. Okay. Each thread is not independent, it is a collection of threads, but they are all knotted at some points, so that they can't go past each other. Okay. Because of the knots, they can only go. So, if this segment between the adjacent knots is sort of coiled up like this, then when you stretch up, that segment actually stretches out. So, the molecules are actually reorganizing when you change the shape. Okay. And that is primarily why it is. I will skip this. I think it is just almost too much time. So, I am going to end now. Okay. So, I will just end by saying a few important things about polymers. Why have they become so indispensable? One thing, is lightweight, it is easy to process and form. You can make all kinds of molded products like buckets, bottles, films, food wraps, carry bags. This is the bad word today. Fibers, textiles, a lot of you are wearing polyester, coating, paints, almost everything today, okay, that we use constantly in our daily lives are made of polymers. So you can't really wish it away. It's going to be around. We have to use it more responsibly. Okay, so it's made life more convenient, but it's also aesthetically beautiful. So polymers in the environment. So what are the positive implications of using polymers? Okay, are there any? I'll tell you there are many. Okay, so the first thing is like wax. Wax melts at 60, 70, 80 depending on the length of the chains. Okay, so polyethylene is basically wax of very high molecular weight. Okay, there's no difference between paraffin wax and polyethylene except the length of the chain. Okay, so as you make it longer and longer, the melting point goes up, and polyethylene has a melting point of about 140 or so. Okay, so which means if you take it to 140, it will melt exactly like wax. You can pour it. So the way you work with wax is exactly the way you work with polymers. And the beauty is that the processing temperatures, unlike iron, which has to be taken to 1200 degrees centigrade, heating anything to that temperature requires a lot of energy, correct? So here polymers are processed typically at temperatures below 200, which means amount of energy required to take it up to process it is far smaller than the amount of energy to process metals or ceramics. So more energy you use, the more environmentally unfriendly you are. Because as of today, much of energy is being generated by processes that lead to carbon dioxide emission. Okay, and therefore it's an environmental hazard. Okay, so that's one big thing. The second thing is lightweight. So imagine you have a bottle, this PET bottles that you buy at home, the large ones are 25 liters. Okay, 25 liter bottles that you buy when you have bulk like that kind of bottle, right? Those things were initially coming in glass. And imagine the weight of a glass container of that size compared to that of a plastic container. So this one, 25, how much is the weight of 25 kilograms of water? 25 liters of water. I guess. How much is I gave you the answer, 25 kilograms, right? 25 liters of water is 25 kilograms. So for carrying 25 kilograms, you will be roughly, if it were a glass container, the container itself will be weighing about 10 kilograms. Okay, so you're carrying 10 kilograms of a container for carrying 25 kilograms of water, the liquid that you need. If you have a PET bottle, the PET bottle will probably weigh about 150 or 200 grams. That means 1/5 of a kilogram for 25 kilograms. So you can see when I'm carrying water, I'm mostly carrying water and the container has no weight effectively. Okay, so which means my transportation costs is going to go down. That means I will burn less fuel for transporting plastic bottles and glass bottles. Okay, so which is the other alternative. So clearly these are two important environmental positives. Many environmental negatives. Okay, so that means is it renewable, etc. People are working on that. Can I have an endless source of plastic? Most important in everybody's mind today is pollution. That means we are throwing away plastic, using them and throwing away very irresponsibly. Okay, so it's not the fault of the plastic, it's our fault that we simply have not educated ourselves adequately to decide how to use, where to use, when to use, and how to discard. Okay, and how to reprocess. So that's the key challenges today that we need to address. Okay, so this is my last slide. Okay, so I've come to the same slide as before. So I'd like to just end by saying material development has been closely linked to the betterment of human condition. We will all agree there's a close correlation between the human condition and material development. As we better understand the fundamental origins of properties exhibited by materials, not my materials, by materials, apologize for that mistake, newer properties and unforeseen applications will certainly result. I have not spoken about many materials like superconductors, for instance. They are still nascent because we don't have a room temperature superconductor still. If we have it, it would be a remarkable development. Okay, so unforeseen applications will emerge, elevating human societies even further. No question about it. Okay, but overexploitation of natural resources in search of new materials, new properties and new applications is clearly impacting our lives adversely. That means when we overexploit our environment, we will have to face difficulties. We have created new problems, ecological and environmental damage and the climate crisis which is looming large. Which means in the process of smelting iron and doing all this, we have emitted so much carbon dioxide and are continuing to emit carbon dioxide into the atmosphere in all the methods that we are using to process these materials, that its impact is going to be very, very severe. Okay? You can't turn the clock back very easily. The time scales over which the changes in climate happens is hundreds of years. Okay? So even if you stop producing carbon dioxide today, you will continue to have the adverse impact of climate at least for another 100 years, okay, before it gradually dies down. So which means we are heading towards more difficult times while we exploit materials for our own benefit. We have caused too much damage already and will continue to cause damage unless we need to be tempered. So we have to progress. Progress needs to be tempered by the conviction to leave behind a clean and sustainable planet. Okay? So with that, I'll thank you all for your attention. I'm glad many of you showed up later. Thank you.
Thank you, sir. I'm sure you all agree with me that the progress of human society is linked to the discovery of new materials. How many materials I cannot even count. Professor told so many things. So in such an orderly way, in the sense starting with metals, alloys, special alloys, and composites kind of thing, nanomaterials, and finally, polymers. I still remember having worked, not directly, at least being aware of certain polymers like polybutadiene, acrylic acid, acrylonitrile in our rocket propellants, or even hydroxyl terminated polybutadiene, HTPV in fact. So very nice. I remembered all those things after listening to the professor. Thank you, sir. Thank you very much for accepting our invitation and delivering this last talk on this theme, origins, as part of our Dasara Lecture Series this year, 2024. And I thank you all for coming to these lectures and encouraging us. We have more lectures regularly, not only for Dasara lectures, we have under different headings. We have lectures, for example, even appealing to small, children like this. So first, before I say anything, and Q&A, which is an essential part of this program, I would request Ms. Sharanya to kindly give the small memento first to Professor Ramakrishanan. Please accept it, sir.
Thank you.
And I request her to hand over the sapling.
Oh, that's lovely.
Yeah.
That would have been just about
enough. Please. So,
thank you.
You only have told us sustenance is very important.
I
so
really
instead
like
of this one bouquet, this is the better one.
Thank you very much. I might need a ride back.
Yeah. Thank you, sir, once again for the wonderful talk. And it's a grand finale for this theme this year. Now we have Q&A. Please, you conduct.
First of all, thank you, sir. Material science, as I can see, everything on the earth is a material, and so it's so vast, and to put everything into one particular lecture is so difficult. So it was really nice. It's a small thought which it just occurred to me. Your name is an alloy, sir. You are one side it is Rama, it's another Krishna, so it's an alloy, sir. So second thing, there are three different questions, sir. About phosphorescence, when we are using so much of this one, that bioluminescence, are we not able to tap it for our needs for light? When we have seen those weaver birds putting small lightning creatures, and so something like that. That is the first question. Second thing, I have also known about this carbon. On the one side it is very light, you use graphite. The other side it is a diamond. It is so hard. And it is really amazing that one side it is soft and it is so hard. So something really unimaginable. The third thing is, unlike like metals, why does this rubber lose its elasticity? Because when after 2-3 years, if I just want to use a rubber, that tension is gone. So,
So, okay, so let me answer all the questions one by one. The first thing is bioluminescence. Luminescence, as fundamentally you should remember one thing, that light is, the substance is emitting light. So, it is giving out energy, okay, in the form of light. So, just applying principle of conservation of energy, you need to supply some energy to the material to get out light. Okay. So, bioluminescence is basically a process by which the organism uses its energy, like we are using energy to talk, walk, everything. It uses its energy to put molecules in the excited state. That means it gives it energy, like in photoluminescence or electroluminescence, we are applying a potential and creating an excited state from which it comes down to give out light. In bioluminescence, the organism is doing biochemical work. It's a chemical process, but biochemical because it's in a living system that generates molecules in the excited state. Okay, so it's supplying that energy and it comes out as light. So I'm not sure what your question was, but that's basically the principle of doing it. So you cannot use that idea in the context of using light emission for a device. One question. So let me answer the other two. The second one was about carbon, graphite and yeah, it's just the nature of the bonding in the structure. Graphite is basically like benzene. You know the structure of benzene. Benzene is a conjugated molecule. It has what we chemists call sp3 carbons. That means it is bonded to 3 other carbons but has one p orbital which can bind laterally. Okay, it forms a pi bond with adjacent carbons. So graphene or graphite is a species that has carbon in sheets, and within the layers there are pi bonds that are present. Like you can imagine, it's aromatic rings that are connected with each other. In diamond, there is no pi bond. It's all sigma bonds. That means each carbon is connected to 4 other carbons through what are called sigma bonds. Okay, no pi bond. There is no p orbitals that are linking, and that gives it a 3-dimensional structure. Unlike graphite, which is a 2-dimensional structure, because it has sp3, and so the interaction between neighboring sheets are weak because there is no chemical bond between neighboring sheets, and that's why they slip past each other. But in diamond, it's a complete 3-dimensional network where carbons are connected to all other carbons. Okay, that means, yeah, that's the second question. And the third question is about rubber, why fatigue happens. And the reason why it happens is nothing is perfect. Okay, that means each time I stretch, as I told you, I'm assuming that no bonds are breaking. You're not supposed to have bonds break if you want complete retraction. So point is, each time you stretch it, some bonds will break, okay, a few of them, but it will not impact the property very much. But as you keep on doing it, the number of bonds that you will break cumulatively increases and they don't recover. Okay, and as a result it will become, that is one thing. The second thing is that being an organic material, both air has oxygen, and oxygen is a very strong oxidant. That means it's waiting to oxidize entities that can be oxidized. And in the presence of light, oxygen and light is a very deadly combination. Okay, that means light gives the energy to oxygen, makes it slightly more reactive. Okay, as a result, it can attack many organic materials. And so rubber on storage is subjected to constantly light and oxygen. As a result, degradation, chemical degradation of the structure begins to happen, and that also causes depletion. So like nylon, for instance, if you keep it in the sun for a long time, after some time it just becomes very brittle. Your nylon ropes no longer have the strength. So that is because of what we call photo and thermo-oxidative breakage of chemical bonds.
There was an online question which asked whether there is a material that is both light and strong. What is the best material that has that property that can be used in, say, rockets or something?
Well, aluminum and aluminum alloys are by and large today's workhorses. But there are lots of organic materials, especially carbon fiber composites. That means carbon, I did write carbon fiber, but you can have carbon, pure carbon based material, which is in the form of a fiber, and that's called carbon fiber. And these are extremely strong fibers, very light. Okay? They are not carbon nanotubes, but they are actually macroscopic fibers. They are micron sized fibers, like hair. Okay? So those fibers, when you reinforce them in a polymeric material like an epoxy, you can generate a composite. And these epoxy carbon fiber composites are extremely strong. Okay? And they can stand temperatures, epoxy can stand temperatures up to over 350 degrees centigrade, 300 to 350 degrees centigrade. So these composites are gradually replacing metal, even aluminum. Okay? But for instance, all your windmill blades, we have large amount of windmills, and those of you who have gone on highways, you will see that the windmill blades are extremely long. They can be probably 50 meters in length, each one. So you have these special trucks that they carry. Those are all made by these epoxy composites. Okay? They are very light but extremely strong. Today, more aircraft parts are gradually being replaced with these epoxy composites. Okay? So that is one replacement that is likely to happen. But there are problems with it, and that is recycling. What do you do after the age is over? Metals are highly recyclable. Okay, that's the beauty about metals. You can easily recycle, you can smelt them back, you can get almost as good property. Although it's energy expensive, you can recover properties very quickly. Organic materials, including the carbon fiber composites, are not easy to recycle. Okay, and so today one of the big challenges is, how do you recycle these? The life of a windmill blade might be 25, 30 years. But at some point you have to do something with those huge number of blades that either break or become brittle or whatever with aging. So how do you handle that is a big question that today people are working on.
Since ages, I think the students of Gurukula, Abhishek Antra Gotirvakara nimgeಲ್ಲ ವಿಗ್ರಹಗಳಿಗೆ ಈವನ್ ಬಾಹುಬಲಿಗೂ ಕೂಡ ಅಭಿಷೇಕ ಮಾಡ್ತಾರೆ. ಸೊ ದೇ ಜಸ್ಟ್ ಪೋರ್ ಲಾಟ್ ಆಫ್ ಮೆಟೀರಿಯಲ್, ಬಟ್ ಎಸ್ಪೆಷಲಿ ದಿಸ್ ಓಲ್ಡ್ ಏನ್ಷಿಯಂಟ್ ಪಂಚಲೋಹ metals, they just seem to retain their properties. That is really amazing. I just want to know how things are retained, and the best example generally they give is that the iron pillar in Delhi, it doesn't rust. How is that possible, sir? Just
that is well understood today, although I am not a metallurgist, so I can't give you a good answer on it. But the fact is that when you mix metals, you get properties that are not the sum of the two. Okay, you get a tremendous enhancement compared to the two components, and that is a synergistic effect that happens. And there's a lot understood from why it happens, how it happens. So much of what we have done in the past, traditional knowledge systems don't have a fundamental understanding. It does not mean that they don't have an understanding. That's something very different. They don't know the fundamental origins of that enhancement, but they have done science in the way they knew best, and that is by changing composition and observing how the property is. Much like Ayurveda, it's the same. We observe, we give medicines, we change medicines, observe, make notes, what happens, what are the comments, and we based on that we write. And so we have formulated not only medications but also material science. We have formulated based on observation of properties. How does it improve, how does it change, making notes. So it was a different system of knowledge generation. But at the heart of it, because we needed basic breakthroughs and fundamentals of physics and chemistry, today we have a much more atomistic level understanding of this. Okay, so credit to our predecessors and our ancestors for having developed that knowledge system that allowed them to mix elements in a way that provided better properties. That's all I can say. I don't have a good answer, but this is basically what I would say. Yes.
So when you talked about LCDs, we have that 16x2 LCD display, right?
Yeah.
Is the same phenomena works there also?
Exactly same. So what happens is each element, when you say a pixel is like a matrix, right? So when you say a number of pixels per unit area, it means how many devices are there, independently addressable devices per unit area. The larger the number of devices per unit area, higher is the resolution, because you can address each element separately. Okay? So what happens is behind each element there is a field effect transistor that drives that element. Okay? So what happens is that independently addressable, that's the key. That means imagine you have a matrix of elements. Each element you can decide whether it should be on or off and what color it should be. Okay? So you can dictate, so the two elements that you can control, the two properties of a display element that you can control is three properties, I would say. One is the color, the second whether it's emitting or not, and the third is probably intensity. I'm not 100% sure, but I'm sure if I have to break it down, I would also want to control intensity. Okay, so there are three of these you can control by controlling the FET, the field effect transistor, that is driving that element.
The voltage you
the voltage you control, the emissivity, that is the light, amount of light coming out you can control, which is the intensity. And then you can either have it, each element having different colors, or you can have a filter in front which you turn on for the color. Okay, so that's the element resolution. So what was your question? I was giving you.
When we apply voltage, you said the alignment
So-
will be straight, right?
Oh no, that is a liquid crystal. So don't forget, liquid crystal displays are gone today because it is a passive display.
We have that LCDs, right? 16x2 LCDs. Those are also work
Okay,
on
so the
same-
LCD is a passive display. Okay, so that means an LCD is not actively emitting light. So let us imagine you want to write a number. If you remember the old LCDs, there are basically 1, 2, 3, 4, 5, 6 and 7
Correct.
for a
We have
number
that,
display, right?
numbering for it.
And each of those can be turned on or off. So an LCD display, by changing the transparency of each element, is either showing you a black color that is there in the back, which turns on. So if you have looked at an old LCD, it's black and white, right? You have either there is color black or it's some opaque color. Okay, you don't see it. So that's an LCD. That's pretty much gone today, because what displays are doing is it's an active display. That means it is emitting light to show the information. It is no longer a passive display. LCD is a passive display.
Yes,
Okay, so today it is active elements, which each element is giving you a color, intensity and whether it's on. And by controlling that in a pattern, you are creating an image. Okay, and in the back of it, of course, is the entire software and the logic circuits that go into controlling the patterns that are present. So you're getting a signal, and that signal is somehow, I'm not an engineer, that signal is somehow converted to all these currents and turn on, off, voltage, everything is controlled to give you the actual display. Okay,
Thank you, sir.
that's the best I can do, not being an engineer myself. Yeah.
Hi, I was just wondering what is the scope of using biological materials like silks and keratins for any of the other applications?
It's huge, okay, that's a huge scope. We've always used it, it's only thing is we are revisiting it. I mean, we have used silk, okay, we have used horse's hair for stitching, before we had these polymers that are degradable sutures, you have various polyesters that we use for sutures today which are used in surgery. We were using horse's hair, okay, the tail hair. We're using it for surgery. I mean, when you want to stitch something. So we've always used naturally occurring materials, a lot of them. That's an example. We have used cellulose, paper for instance. We have used silk for fabric. We've used many things. Today there is a resurgence of interest in going back to it. Now that we understand many more things, and we have biology at our fingertips, basically. That means you know how to modify organisms, how to change the genetical makeup of organisms. We have all these tools now. So in principle, tomorrow we will be able to modify genetically to produce materials in principle with desired properties. Okay, it's not far away. I expect they are doing it a little bit, but I expect tomorrow we might be able to generate potatoes that are directly injection moldable. Okay, so it's feasible, I'm saying. Today you can't mold potato, you can't melt potato and form it in whatever shape you want, right? But it is not inconceivable that tomorrow you can generate fruit, or basically what you can, and directly put it in a molding machine and convert it into objects that you want. Conceivable.
But what's the bottleneck in using them right now, majorly?
Oh, there are many bottlenecks. One is we don't understand fully how to do it. Second is it does not have the properties that you desire as of now. Like polyethylene and polypropylene are incredible materials. Okay, they are extremely high strength. Today, you know, all your knee replacement, if you have a knee replacement, those are made by high density polyethylene, ultra high molecular weight, high density polyethylene. Extremely low abrasion, that means highly abrasion resistance, very low friction, very high properties. Okay, we don't have any natural material that can replace it today. Sorry? Spider silk is good, but how do you, well, there is a company in Pune which is started by an Indian company, an Indian entrepreneur, a woman entrepreneur, who's doing exceedingly well. Okay, I forgot the name of the company, but she has learned how to process silk. The point is, silk is a polypeptide, a polyamide, okay? So it's like protein, it's a protein. You can't melt proteins, okay? You can't melt proteins. But she's figured out a very interesting way when she did a PhD, is how to process, convert it to a liquid. That means make a solution of silk and then reconvert it into various objects. And she has floated a company which is beginning to do well, mostly on materials based out of silk, with different porosity, strength, everything tunable, but pure silk, nothing else in it. And you can use it for bone graft, where tissue will grow within the fiber, and it is completely biocompatible. So it's coming. Yeah.
I just wanted to ask, since LEDs are based on the polarization, is that why we see some display when we tilt it or see it from some other angle?
Okay, so
when we change the alignment of the display?
No, but there were two things. The display that I gave, no, it's not an LED actually. The display which I talked about was a twisted pneumatic liquid crystal. That's a passive display. But what you're saying is slightly different. That means the emitted light from these materials, are they polarized at all? Okay, typically they are not polarized. Okay, unless you have molecules that are oriented. Typical LEDs based on inorganic materials are not polarized. They are apolarized light that comes out. But what you are seeing by different directions is most likely due to the front layer which is present on top, which may have some, because you can buy today sheets that you can put on your on your laptop screen, which will prevent people from seeing from an angle. That is basically structured films. They are basically films that have been micro or nano structured. They have structures. They are not flat. It looks flat, but they have lines. And those lines allow light only come straight. But if you go slightly, because the lines are there, you can't, light doesn't come through, it's reflected. Okay, so it's basically a structured film on top that causes this effect that you can have, you can see it from one direction and not the other.
So it's not a polarizer, but it's blocking the light.
It's a structured film. Imagine something that looks like this. Okay, so let's say something that has lines like this. So light can easily come. If light is coming from here, light can come straight. But if light has to go this way, it will hit the wall here, right? So it will not come out. So it's basically reflected back. So basically it's a patterned film that creates it. I think you have all seen this three-dimensional thing. You can have a film that you put on a drawing, and then you can see that different things are seen from different sides, right? So imagine that it is a slightly different variant of that. You see, the reason you're putting a sheet on top of on a drawing, and when you come this side you see something else, when you come this side you see something else. It is simply because of the patterned substrate that is on top of the painting. Okay, so it's very similar to that.
If there are no more questions, we'll end the talk.
All right.
Yeah, I'm here to formally present the vote of thanks and formally close the event or close this series of lectures, what's named of the Dasara Lecture Series. So, as actually the natural world around us fascinated us, and by observing them, we accumulated so much of knowledge, right, which actually made us to wonder about what actually the place we are living in. And similarly fascinating was the applications of the knowledge that we accumulated over these years through our observations and so on. And much more fascinating is the thing which, using these the sciences that we accumulated, we can playfully create many things, right? And we can do many things what we can think of. So today we had Professor Ramakrishna with us, who actually told the fascinating stories of materials, which actually, how actually they behave, and the various beautiful things of the nature, naturally available material, and also many man-made materials. So, on behalf of Jawaharlal Nehru Planetarium and also the audience, I heartfully thank you very much for presenting this talk, sir. Thank you very much. And also, the 4 lectures that were presented attracted many audience, right? And all the 4 lectures were extremely very attractive and also very informative. So I thank all the audience for being present with us all these 4 days, or in all these 4 lectures in their series, what we call as the Dasara Lecture Series. So we will be having many more lecture series in different names, as our director mentioned. So please, we expect you to come to those events and also become play a supportive role and encourage us to conduct more and more such programs. And I think I will hand over the mic to our director to say a few words.
The onus of responsibility of announcing the snacks outside, again, he forgets every time. Okay, kindly do have snacks and have coffee. I always say he will make an important announcement. So this is the second time I am making. Anyway, so all said and done, thank you very much for your support. And we have lectures appealing to different level of students, okay? Students at different levels. So we have many things which are conspicuous, okay, appealing to students of all ages, okay. Kindly do come and have a look at our website. If there is any lecture or anything on a particular day, especially on Sundays, we'll announce, and we request you, some of you to become JNP club members, in fact, so that it's nothing, in fact, in terms of monetary thing. But you can, what can I say, you can involve yourself more with this kind of activities. And yesterday I announced from next Sunday, that is every 3rd Sunday of every month, we are screening from next 3rd Sunday onwards, we are screening Carl Sagan's Cosmos. Okay, kindly do come and enjoy that. And in a big screen, if you were to see, definitely it will be a blissful experience. So kindly do encourage us, attend all our lectures, tell your friends and others. So kindly do support us. Thank you very much. Thank you, sir, once again.